use MCMC algorithms to obtain samples from our posterior, and then we can approximate the posterior with point masses at our samples, and we can estimate any quantity of interest, such as the predictive distribution. So how do we construct this MCMC? We can use the Metropolis-Hastings algorithm, so we just need some proposal density Q. We generate a candidate from our proposal density, and we accept with this acceptance probability. If we accept, we set our new state equal to our candidate value, otherwise we keep our current state. And we show that this satisfies the detailed balance condition, so all of the nice theory holds. So what kind of proposal distribution, how should we specify the proposal distribution? We saw 3 different ways of doing this: the independent Metropolis-Hastings, random walk, and Gibbs sampling. So independent Metropolis-Hastings was the first example we looked at. This is when the proposal doesn't depend on our previous state. So in this case, one example could be, so what we're interested in doing, okay, suppose we have a model, xi given theta, or IID, with some density, which depends on some parameters theta. Theta has some prior, and what we want is we want posterior inference, but this is unavailable. So one way we can use independent Metropolis-Hastings, and we can just set our proposal equal to our prior. So this is one way of using independent Metropolis-Hastings. What would our acceptance probability be in this case? So our acceptance probability can you see this marker? Is it? Thanks. Yeah, that's better. Okay, so our acceptance probability, it's our target, which is our posterior, evaluated at our, sorry, this is not x, this is theta. So our candidate, given the data, our current value, given the data, times our prior. So in this case, things cancel out a bit, right? Because we can write the we can write the posterior as the prior times the likelihood divided by the marginal of x. Same thing here. We have the prior times the likelihood divided by the marginal. And we can bring this term down as well. And you see that some things cancel out, the prior cancels out. So we just accept with the, this is theta star, theta t. We just accept with probability proportional to the ratio of the likelihoods. So this simplifies to and then we can just erase some things. And we have the ratio of these two terms here. So this is bigger than 1. if we our acceptance this ratio is bigger than 1 if we've proposed a new value which fits our data better. So this is one way of implementing the independent Metropolis-Hastings sample algorithm when in Bayesian inference. Okay. Then we saw the, okay, so sorry, just to go back to the independent Metropolis-Hastings algorithm. So in this case, we want this acceptance probability to be high. So we want to find this proposal density because we know the expected acceptance probability is bounded below by alpha. So we want a high acceptance probability in independent Metropolis-Hastings algorithm, which means we want to find a Q which is as close as possible to our target. Instead, in random walk, we just propose a new value which is close to our current state. So this leads to this acceptance probability, which again, it's a ratio of these two terms here. So in this case, as opposed to the independent Metropolis-Hastings algorithm, we don't want an acceptance probability which is very high. We want a moderate acceptance probability. A rule of thumb would be between 0.2 and 0.5 because we don't want to explore, we don't want to accept too much. That means we're not exploring our space enough. And we obviously don't want to reject too often because then the algorithm's inefficient. Okay, and the last algorithm we saw was Gibbs sampling. So Gibbs sampling is actually a Metropolis-Hastings algorithm. We didn't show this yesterday, so I'm going to show this real quick just to clear up any confusion. So Gibbs sampling, we can see this as a Metropolis-Hastings algorithm. So let's say our current state, xt, is equal to x1t. So we have d variables here. That's our current state. At each step, we propose a new state, x star. So let's just say we're updating the first element. So we propose a new state and we keep all the others the same. Okay? So we can see this as a Metropolis-Hastings where our proposal is we sample x1 star conditioned on the current state of all the other variables. And we just set all of the other variables equal to their current state. So it's a point mass at our current state. Okay? Now, in this case, what's our acceptance probability? Our acceptance probability is, again, we have the minimum between 1 and the ratio. So we have our target evaluated at our proposal. divided by our target at our current state times the ratio of the proposal density. So we have this one on the bottom, and on the top, we don't need these indicators because we've set these equal to the current state. So you can see that in this case things cancel out, so that this is 1 and we always accept. So let's just show that. We can rewrite this first term here. See that this term is just the joint over the marginal just from the definition of conditional probability. We can do the same thing here. Over the marginal. So you see that these marginals cancel out and that these terms cancel out with these two terms here. So we get an acceptance probability of 1. So Gibbs sampling is just Metropolis Hastings, where we always accept. Okay, then we saw an example of Gibbs sampling. This was probit regression. So in this case, we don't have a closed form for the posterior of W, but we can introduce this latent variable y tilde, and we can use Gibbs sampling, and we have these nice conditional on y tilde. The posterior, or the full conditional of W has a nice form, and similar, we can sample y tilde. It's just a truncated normal. Okay, so now let's look at logistic regression. So logistic regression, it's very similar to probit regression, but instead of so it's just a different way to map this linear function to the unit interval. So instead of using the probit function to map the linear function to the interval 0, 1, I'm using the logistic function, or the logit function. So we'll consider the same prior on W. In this case, as Miguel discussed last week, we can also represent this model in terms of a latent variable. So if you remember, Miguel showed this last week. He showed that we can introduce some yi tilde, which is equal to xi transpose w plus some epsilon I, where these epsilon i's are independent with a logistic distribution. The problem in this case is that we can't use Gibbs sampling, because if we look at the full conditional of W given these y tildes, it no longer has a nice form, because this is not a normal distribution anymore. So one algorithm we can use is the random walk. So this is, okay, here's one proposal. So we just have a normal, our proposal is a normal distribution centered on our current state. And here for the variance-covariance matrix. So this is similar to what we saw in the updating rules before with the normal distribution here. So what what they do in this algorithm is just to replace what we saw before, x transpose x. This C hat is the variance covariance matrix of the maximum likelihood estimates. So they first find the maximum likelihood estimates, extract the variance covariance matrix, and plug that in and use that for our variance covariance matrix in our Metropolis Hastings random walk. This matrix V is a diagonal matrix, and the elements of it are some tuning parameters which we choose. So you can start off, say, setting the diagonal equal to 1. You can run this this random walk algorithm, and so this function is implemented in the R package called MCMC pack. The function is called MCMC logit, and as an output, it will tell you what the estimated acceptance rate is. So if your acceptance rate is too high, then you can rerun the algorithm adjusting this matrix V appropriately. And a nice thing about this R package as well is that, so it gives you out an MCMC object, and there's another R package. It's called CODA. So this R package has many diagnostic tools for assessing convergence of your MCMC chain. So it has a summary function which outputs the quantiles, the expected value. It has a trace plot. You can see the trace plot's the autocorrelation plot. There's also many other diagnostic tools to assess the convergence. Okay, so here is an example. So I simulated some data based on the true model. I ran this. I got an acceptance probability of roughly 0.5 in this example. So here's the trace plots. You can see the mixing is okay. The autocorrelation plots, it's a bit higher in this case, so maybe I should play with that matrix V a bit to reduce the acceptance probability. We can see if we compare with the probit, the chain looks a bit stickier for this logistic problem. And here is just my estimated, say, regression function, or the probability y is equal to 1, the predictive probability that y is equal to 1. So the red is the true curve from my simulated data. The black is my estimate. And again, these are the 95% point-wise credible probabilities around the mean. So here was my data here, the crosses. The x's were zeros, and the circles are ones. Okay, so here's just two references. So these are quite nice papers. They explain things very well. They're very clear, so if you want further references, you can check out these papers here. Okay, so now we'll see two examples. Two exercises. Okay, so the first exercise is just an extension of the probit model to a multi-class setting. And then the second example that we'll look at is using a spike and slab prior. Okay. So this is known as the independent multinomial probit. So in this case, yi, our output, takes values in 0 to k. So we have some input, and we introduce a latent variable, yi tilde, such that, so this is a k by 1 vector, where yi tilde 1 is equal to w1 transpose xi plus some error yi2 w transpose xi plus some error yi tilde k okay, and these errors here, these epsilon I, j, are IID normal 0, 1. Okay, and then we say that our output y is equal to, so if it's equal to 0, if the max of yij tilde is less than 0, or let's say less than or equal to 0. So if all of my latent y's are less than 0, I set my output equal to 0. And it's j if yi tilde j is equal to the max of yij tilde, which is bigger than 0. Okay, we can marginalize out. We can marginalize out the yi tildes, so we get what our model is. So the probability that yi is equal to 0 given w and x, well, that's just the probability that all of my latent variables are between 0 and negative infinity. So normal yij tilde has mean wj, variance 1, dyi tilde. So this is just the product from j equal 1 to k of, and this is just the standard normal function. It has about 0 minus the mean divided by 1. So this is just equal to the product from j equal 1 to k of 1 minus phi of wj transpose xi. We can also find the probability that yi is equal to j. So what is this probability? This is the probability that the jth latent variable, yij, well, that must be between 0 and infinity. And all of our other latent variables can be anywhere between negative infinity and yij tilde. Okay. So again, we can compute this, and we have the product for j, let's say j prime not equal to j, of phi of yij tilde minus wj, wj tilde transpose xi divided by 1. And then we have to integrate this. Okay. So now we need a prior on W. So our prior on W, we'll just take Wj, or IID, normal, W0, sigma 0. So you can see that if I try to compute the posterior of Wj, I will get something that does not have a closed form solution. Even at this stage, we don't have a closed form for the likelihood of yi equal to j. So we'll use Gibbs sampling methods. So the Gibbs sampling algorithm. So the first step, the step 0, is to initialize our chain. So we need to initialize y tilde and w. Step 1 is to sample w from its full conditional. So w given the y's, the latent y's, the y tildes, and the x's. So let's calculate what the posterior of w is. The posterior of w this is proportional to our prior on w, and the likelihood of y given the w's and x, the latent y's. Because our output, our observed y's given the latent y's, is just deterministic. So this here, this is the product from j equal 1 to k, normal wj, w0, sigma 0. The second term is the product from I equal 1 to n, the product from j equal 1 to k, and then we have a normal yij tilde, wj transpose xi with a variance of 1. So this just looks like the normal updates that we saw in the previous lectures. So you can figure out what the posterior is in this case. It's just a normal with our usual updated mean and variance covariance matrix. So this variance covariance matrix is our prior plus x transpose x inverse. And our updated mean is just sigma hat j times sigma 0. I called that W0. Okay, so this is the usual updates. So this is y tilde j. So y tilde j is the vector of yij tildes. So this is an n-dimensional vector. Okay. Let's see, I'll erase this. Okay. Now the second step, step 2, we need to sample our latent y. So we sample y tilde given our weights, our observations, and our data. So the full conditional of y tilde, this is just proportional to p of y tilde given x and w, and p of y given y tilde. So this we saw before from over there. This is just product from I equal 1 to n, product from j equal 1 to k, normal yij tilde with mean wj transpose xi, variance of 1. So this second term, this will be our truncation term. So this is the product from I equal 1 to n. So if all of the yi tildes are less than 0, so I'm using this notation here, just short notation. So this is 1 if yi1 is less than 0, yi2 is less than 0, and yik is less than 0. So we need all of our yi tildes to be less than 0 if our output is 0. And we need that yij tilde is bigger than or equal to the max of yij tilde, which is bigger than 0. And this is if our output is equal to j. So you can see we still have this product from I equal 1 to n. So this means that conditioned on everything else, these yi tildes are independent across I. So we can sample yi tilde independently. So for I equal 1 to 0, if yi is equal to 0, we sample yij tilde independently from a normal with mean xi transpose wj, variance of 1. So this is truncated normal, and Yij tilde must be less than 0. So in this case, if yi is equal to 0, we just sample all these latent Yij's from a truncated normal where the truncation point is at 0. Now if yi is equal to j, then we can proceed by first sampling the Yij. Let's see. Just write it over here. So if yi is equal to j, we sample first Yij tilde, and this is from a normal, again, centered at xi transpose wj, variance of 1, and we just have, we have the normalization constant there, and we just have the indicator that this must be greater than 0. So this is from a truncated normal, where now the truncation is at 0, but it must be on the other side. And then for j prime not equal to j, we sample Yij prime tilde, and this is from a truncated normal, so now the truncation is that Yij prime tilde must be less than Yij tilde. Okay. And so that's the Gibbs sampler for the independent multinomial prior. So one extension of this is to, instead of assuming that these errors, so you can see that these errors here have a multivariate normal distribution with a diagonal variance covariance matrix with 1s on the diagonal. So one way to extend this model, which is just known as the multinomial probit, is to have a general variance covariance matrix. So one of the problems with that is that in order for the model to be identifiable, we need that the first, so we could extend this by saying yi is normal 0 with some general variance covariance matrix. In order for this to be identifiable, we need, say, the first element. So we need sigma 1, 1, 1 equal to 1. But you can do the update in that case. In this case, people usually put a prior also on this sigma, so it's difficult to find a prior on this, which enforces this constraint here. And then when you look, the only change, the updates change. One change here is that you would have to sample from a truncated multivariate normal here, so you need to change these steps as well. Okay, so let's look at the second example. All right, I'll erase everything. So the second example is a spike and slab prior. So that's when we want to encourage some of these weights to be close to 0. So this is popular in settings where x has a high dimension. start with the references. So exercise 2. So this is the model. I took this exact model, the sampling scheme, from, well, the model was first introduced in 1993 by George and, let me make sure I spell this right, McCullough. And then there's later improvements to the model. So in particular, we'll be looking at this 2005 paper by, the other way around. Ishwaran and Rao. So they have several papers, I think 2000, 2003, 2005. They're basically all on this same model. Oops, forgot a 0. Not the year 200. Okay, so here's the model. We'll consider that we're in the setting again when our output takes values in 0, 1. So yi given xi and our weights is, we'll just use our same probit model as before. But now we want to put a prior on these weights, which encourages them to be close to 0, or some of them close to 0, for unimportant input values. So one way to do this is to say that the prior on wj conditioned on tau and p, we'll see what these are in a second. This is independent. This is independent, and it's a mixture of 2 normals So it's a mixture of 2 normals. This term here, so this V naught is fixed. It's fixed and it's chosen so it's very small. So that this is a normal, but it has a very, very high mass at 0. So this is our spike term. This will encourage, with probability P, these weights to be close to 0. Instead, we have the slab term, where in general this tau j will be large, so that this term here is a normal. So we have our prior on W, we have a mixture between something with a high mass at 0 and another normal. So another formulation of spike and slab priors is to put a point mass at 0. Here we'll consider this case because we still have a continuous prior on W in this. And if we put a point mass, it's no longer continuous. Okay, we need priors on tau and P. So tau j, we'll assume that these are IID. This is inverse gamma with parameters A1, A2, and P is beta, B1, B2. Okay, so this is our model. Again, I'm going to rewrite it a little bit and introduce a latent variable which will help in our sampling. So in particular, I'm going to rewrite this line here. Okay, so I will introduce a latent variable, Cj. Cj given P is with probability 1 minus P. It takes value V naught. And with probability P, it takes value 1. Then Wj given Cj and tau j is normal 0 Cj tau j. Okay, so now if we integrate out Cj, we should get back to our original model. I think that's correct, right? No, wait, it should be tau j here, I think. I think I wrote this wrong, so this would be so if I integrate this out, I have V naught times tau j, or I have tau j. Yep, that's correct, right?
So what is this variable, Cj?
Cj is just a latent variable, so with probability 1 minus P, it's equal to V naught. And with probability P, it's equal to 1. And then I say that Wj given Cj and tau j is just normal with this variance here. So let's just make sure, let's integrate out Cj. So Wj given tau j and P should be equal to the integral of Wj given tau j, Cj, and P of Cj given tau and P. Okay, this is normal 0 Cj tau j, and this with probability 1 minus P, it will be V naught. So with probability 1 minus P, this will be V naught, and with probability P, it will be 1. Oh, sorry. Does everybody see that? So that's correct. Now.
So this second variable basically tells you whether nothing is sampled from one of the clusters.
Yes. I'm going to erase this line. Okay. So now we can write out our Gibbs algorithm. Okay. So step 0 is always to initialize. So we have a lot of variables in this model. What do we need to initialize? Well, we need to initialize our. We'll introduce the latent random variables y tilde to deal with the probit. So we need to initialize y tilde. We need to initialize our weights. W. We need to initialize the taus. We need to initialize the C's. And we need to initialize P. So we're going to have 1, 2, 3, 4, 5 steps in our Gibbs sampler. Okay. Let's start with the W's. So we want to sample W from its full conditional, so given all the other variables, which are tau, C, P, Y tilde, and our data. So all the other variables and our data. Okay, this is just proportional to this is proportional to our prior on W. So this only depends on C and tau. And the likelihood of Y tilde given W and X. Okay? So this is a normal. I'll say a normal 0, D. Now what's D? D is a diagonal matrix with elements Cj, tau j along the diagonal. Okay? And now we have our likelihood. So this we can write as normal Y tilde given XW with identity matrix. So instead of writing it as the product from I equal 1 to n, I just rewrite this. X is a n so if xi has dimension d, this big matrix X is n by d, so the ith row is the input values for the ith subject. Okay, this is just the normal updating rules that we should be used to by now. So this is just proportional to a normal with updated mean and variance covariance matrix. Again, we can write out what these updates are. See, I'll write it up here. So sigma hat is equal to sigma plus X transpose X inverse. Oh, this is sigma not. Oh, sorry, that's D. That's our matrix D. D inverse plus X transpose X inverse. W hat is just equal to, so in our usual updating rule, we had a mixture between the prior and the maximum likelihood. The prior is at 0, so that term goes away. So what we have is just sigma hat times X transpose Y tilde. Okay, we're ready for our next step, step 2. Step 2. So step 2, we will sample the C's. So sample C, given all of our other variables. We had W, we had tau, we had P, Y tilde, and our data. So the full conditional of C This is just proportional to our prior on C, which depends on P, and the likelihood, or the W given C. Okay? So this term is just this up here. So we have the product from J equal 1 so we need to say what's the dimension. So if the dimension of X is, let's say, D, this is the product from J equal 1 to D. And this is a mixture of a point mass at V naught and a point mass at 1. So we have this term, and then we have W here. So this is just the product from J equal 1 to D. And then we have a normal WJ, 0, CJ, tau J. So if you work this out, what you will get in the end is that we have the same form for the posterior with updated probabilities. Okay? And this P hat is equal to, so this is P times this normal as proportional to WJ. So this is when CJ, P hat is when CJ is equal to 1. So we have the normal, which is EXP negative WJ squared. So if CJ is equal to 1, we just have a variance of tau J. And then we divide. Okay, and this is when CJ is equal to V naught. Okay. So this is the normal we get when CJ is equal to 1. This is the normal we get when CJ is equal to 1, and this is the normal we get when CJ is equal to V naught. And we can ignore the normalizing constants in the normal because they cancel out. Okay? Let's see. Okay, step 3, let's update tau. We sample tau conditioned to all the other variables, which were W, C, P, our latent Y, and our data.
I think in this case, the normalization constant, there is at least some factor that you cannot eliminate because